So, we will be discussing now the transformation of the coefficient of second fundamental form. So, suppose the parameter of a given surface are u 1 u 2 and we change them to u 1 dash u 2 dash. So, now we are interested in seeing how the coefficient of second fundamental form will change. So, if you remember, the Bij's coefficient of second fundamental form are also defined by this formula n I dot r j. So, let us see, suppose n dash I denotes the derivative of n with respect to the coordinates u I dash. Okay. So, this if you I can rewrite as del n over del u j or del u k into del u k upon del u dash I. By chain rule you can write like this: del n upon del u k you know is n k into del u k over del u dash I. So, n dash I is this much, n dash I is n k into del u k over del u dash I, where k is a dummy index over here, that you can easily see. Now, next I will see how r j transform. So, with that we already know the transformation of basic tangent vector r dash j suppose. So, by definition this is del r over del u dash j. This again by chain rule you can write down del r upon del u k something L into del u L over del u dash j, that is R L into del u L upon del u dash j. So, this is how R j transforms. Okay. Take the dot product of n dash I and r dash j. So, taking dot product, I will be having in the left side n dash I dot r dash j. Writing down the values, I will be getting n k. Here I have a okay, and I dash is n k into del u k upon del u dash I dot r dash j is here. This is r L into del u L upon del u dash j. So, this brings n k dot r L will become b k L in the dash non dash system, sorry, into del u k upon del u dash I del u L upon del u dash j. So, this becomes your b dash I j, and n k dot r L is also minus times b k L. So, this minus you can remove. So, you have this law of transformation for b I j. So, this is the law of transformation for the coefficient of second fundamental form. Now, I can think of b also, as we know that b equal to b 1 1 b 2 2 minus b 1 2 square, that is determinant of b I j. Now, if I want to see how b transform from non dash to dash system or the other way around. So, b, what will happen to b? Suppose in the coordinate system u 1 u 2, the determinant of b I j is b, and in the new coordinate system u1 dash u2 dash, the determinant of b is suppose b dash here. So, what is the relationship between b and b dash, that we would also like to see. So, b dash, let me write down. So, b dash should be equal to b dash 1 1 into b dash 2 2 minus b dash 1 2 square. Okay. So, okay, why should I do like this? I can write down directly. We have the formula here in the box. So, this is b dash I j is equal to b k l into del u k upon del u dash I del u l upon del u dash j. What do? You take determinant in both sides. So, taking determinant in both sides, gives determinant of b dash I j, I will call b. In the right side you have determinant of this matrix into determinant of this matrix into determinant of this matrix. So, that will be equal to determinant of b k l will be simply b into determinant of del u k upon del u dash I into once again determinant of del u l over del u dash j. Okay. Both the matrices are same in fact. When you will take the determinant of the two, you will get determinant square of this matrix b into, I can write down this matrix as del u k l u l upon del u dash I and u dash j. This notation you understand. So, square of this. Okay. So, this is how b dash transform. So, this is the law of transformation for b square. And you square it. This is a matrix, this is a matrix, this is a matrix, and then you take its determinant and square it. This bracket does not make much difference. Okay. All right. Now, if you want to see how the Gaussian curvature transform, whether it remains same or it changes in the new coordinate system, that can also be seen. Now, let me recall the transformation of G. If G dash is the determinant of G I j in u 1 dash u 2 dash system. So, this we remember it is equal to G into once again the same determinant square. Sorry. Okay. Now, what is the Gaussian curvature? Suppose the Gaussian curvature of a surface in the new coordinates is k dash. So, this must be equal to b dash dash in the left side, dash in the left side. upon g dash. Now, both the values are available to us. So, this will become simply b upon g, that you can easily see from the last two expression. So, this proves that the Gaussian curvature remains the same in the two coordinates. Okay. So, this is one thing that we would like to see all the time. Whenever you have a geometric invariant, you all the time try to see if the coordinates are transformed, whether the quantity remains the same or it changes. So, this Gaussian curvature remains the same. Okay. Now, one more point was left last time, that is some special points on a surface. So, the second fundamental form, let me recollect, it was defined as B11 into du1 square plus 2 times B12 into du1 du2 plus B22 into du2 square. This is a quadratic form known as second fundamental form. Now, this quantity may be positive definite or negative definite or indefinite or sometimes 0 also, and it may change from point to point. So, let us see, let me rewrite down this expression as B11 into du1 plus B12 into du2 whole square and plus B11 B22 minus B12 du2 square. Now, the whole thing I divide by B11 and see, do you get the same quantity? You can check it up whether I have written it correctly or not. This is the same. So, this in fact is the same. Okay. Now, when this is positive definite, this is a quadratic form, this is a natural question whether a quadratic form is positive definite 0 or negative definite or something indefinite. So, you see the first bracket here as a square. So, it will be positive if this quantity is positive. Okay. And if you remember, this quantity is B, it is in fact determinant of B I j. So, the second fundamental form, let me write down a definition in fact here. And these quantities are defined only at a point, they may change from point to point. So, a point number 1, a point P over a surface is said to be an elliptic point if B is strictly greater than 0 at P. Okay. And it is said to be B, you can see the quadratic form will be positive definite if this quantity is positive. I will call such a point to be a elliptic point, and number 2, a point P over a surface is said to be a parabolic point if B is equal to 0 at P. And number 3, the first line is same, a point P over a surface is said to be a hyperbolic point if B is negative at P. So, this is a classification of point. You can encounter all these 3 points. What geometrically you can see in the first case, for example, you will see the tangent plane would lie around the neighborhood of the point P only on one side of the surface, because your surface may be like this. So, you may have a tangent plane whose some part is below the tangent plane and some part is above the tangent plane. So, we will say that a point P is elliptic if the plane lies only on one side of the surface around that point. Okay. In this case, what will happen? In this case, the tangent plane and the surface will have something common, and the common thing will be some curve. Is it right? For example, if you look at the tangent plane of a cone or a cylinder, you will see the entire line is common between the tangent plane and the surface. Okay. And the ratio of du1 over du2 remains the same throughout the neighborhood. Similarly, you can see this is somewhere it will be negative, means the surface will be below the tangent plane. Okay. All right. So, these are some special points that you will notice while studying a surface. Now, I come to the next topic, that is the Gauss and Van Garten formulas. Gauss and Van Garten formulae. Please check it up if anything is left before Gauss and Van Garten formula. Do you have something? Some exercises can be noted down at this point. Some exercise before coming to the Gauss formula, we have some exercises. For example, you would like to see whether the Gauss curvature of a plane is 0 or not. The answer is yes. This is something to be done. The Gauss curvature of a plane is 0 at all points, We would also like to see what is the Gaussian curvature of a sphere. So, the Gaussian curvature of a sphere of radius a is 1 over a. 1 over a or 1 over a square? Perhaps it is 1 over a square. It is 1 over a square. Okay. And the Gaussian curvature of a surface of revolution, Gaussian curvature of a surface of revolution that you can compute. Okay. So, show that. All these things, and in particular you can find out the Gaussian curvature over here for a sphere, that you can notice that it is 1 upon a square, okay, because a sphere is also a surface of revolution. Okay. First one is easy, because the formula for Gaussian curvature is B upon G, and you have seen for a plane the coefficients of second fundamental form are all 0. So, therefore, determinant of B I j will be 0. Since the numerator is 0, everything will become 0, and other calculations are simple. I do not think I should work it out. I have done some problem last time, so I stopped. That is right. Yes, that is right. Yes, we have done problems on the computation of B and computation of G. So, this is not new. Okay, let me come to the Gauss and Van Garten formula. Should I give you a break at this point, if you see how much time